Okay, in this video we're going to finish the theorem about identifying internal direct products. So just as a reminder, the theorem is if G is a group and contains subgroups H and K satisfying number 1, H and K are normal in G, and 2, H and K intersect trivially, that is, they intersect only in the identity element of G, then HK is a subgroup, and HK just means the set of all elements that can be written something from H times something from K. This is a subgroup of G, and it is isomorphic to the external direct product of H and K. And again, this time symbol here means the external direct product with all the bells and whistles, like the ordered pairs and the ordered pair arithmetic, and so on. All right, so what did we do last time? Last video we showed that HK is indeed a subgroup of G. And for that, we needed to use the fact that H was normal. We actually didn't need both H and K to be normal. We just needed H. Probably could have done with K as well. But here's where we're going to use the fact that H and K are both normal. All right, because now we're going to show that there's an isomorphism phi from H cross K to HK. And here's how we're going to do it. We're going to define phi from H cross K, the external direct product, to HK, this internal direct product, by phi of H comma K equals HK for all HK belonging to H cross K. In other words, for all H belonging to the subgroup H, all K belonging to subgroup K. All right, that's pretty much the same thing that we did in that video involving the units mod 15. It's the same idea, except here we're not guaranteed that G is an abelian group, so we're going to have to be careful about a couple of things. So one of the things we have to be careful about, of course, is if we say define phi by this and this and this, and say it's an isomorphism, we better prove it's an isomorphism. So that's the rest of this proof. Need to show phi is an isomorphism. All right, so to do that, we're going to show that phi is a homomorphism. We'll show it's 1-to-1. We'll show it's on 2. Let's start with the easiest one first. The easiest one, and I don't mean to say that anything in abstract algebra is easy, but if there is something that's easy in this proof, it's this. To show that phi is on 2, to show that phi is on 2, well, observe that if y belongs to hk, so some possible target of this function belongs to hk, then y is equal to h times k for some h in the subgroup H and some k in the subgroup K. Okay, then we know that phi of hk is equal to hk, which is equal to y. So really, just by definition of what hk is, we know that this map is onto, because anything that's in here is going to be something from H times something from K, and then once we know that, we know exactly what order pair gets sent to it. So phi is on 2, and that's not really such a big deal. I want to show that phi is 1-to-1, because it's actually a really nice trick for doing it, but to do this trick, I need to first show that phi is a homomorphism, because I want to use the kernel to show that phi is 1-to-1, and for any of that stuff to work, I need to know that I have a homomorphism first. So let's go on and show that phi is a homomorphism. There we go, is a homomorphism. Well, let's suppose that we have two elements of H cross K, H1, K1, and H2, K2. And we need to show, as always, that phi of H1, K1 times H2, K2 equals phi of H1, K1 times phi of H2, K2. I feel like I should write that down. There we go. That looks a lot better. Sometimes you just say something and it just comes out as a mouthful. Now, one thing I'm doing here that you might notice is really what goes in the parentheses here should be an ordered pair. An ordered pair should itself be surrounded with parentheses. But sometimes it's common practice to just collapse a couple of sets of parentheses and just do one set of parentheses. And I'm going to avail myself of that privilege here. When I say phi of H1K1, I mean phi of the ordered pair H1K1. I'm just trying to avoid having to do double parentheses all over the place. Okay, so let's see if we can prove this. Let's start by calculating the left-hand side. I am using double parentheses inside this one just because I want to watch the arithmetic take place inside the function argument. So if I calculate the product of those two ordered pairs, I get phi of H1, H2, K1, K2. And then the way we calculate phi here is pretty straightforward. We just take those two elements and jam them together. So that's going to be equal to H1, H2, K1, K2. All right, so far so good. Now, what about the other side? The other side is going to be phi of H1, K1 times phi of H2, K2. And that evaluates to H1, K1, H2, K2. And now we reach an interesting little precipice here. Are those two elements the same? Hard to say. G is not necessarily abelian, so we can't do that this time. So now I feel like I'm a little bit stuck. Because I have no abelian group to allow me to commute H2 and K1, and yet I need those to commute for this thing, this phi, to be a homomorphism. So it looks like I have no choice. At this point, it's time to bust out the commutator. Okay, we haven't talked about commutators in the videos yet, but here's what a commutator is. The commutator of x and y in G is the group element, and sometimes it's written as brackets x comma y. That's a notation we sometimes use for it, but it's defined to be x, y, x inverse, y inverse. Okay, that looks crazy, right? Why would we care about such a thing? Well, here's why we care. X and y commute if and only if the commutator of x and y is the identity. X and y commute if and only if xy equals yx, which is true if and only if, well, let's just multiply both sides on the right by x inverse. That means xy, x inverse is equal to y, and you could reverse that step as well. And then multiplying both sides on the right by y inverse gives me xy, x inverse, y inverse is the identity. So x and y commute if and only if their commutator is trivial, if and only if their commutator is the identity. That's what I'm going to do with H2 and K1. I'm going to calculate their commutator, or try to say something about it, try to show that it's the identity. And I claim that if I do that, I think we're going to get unstuck here. All right, so let's come over here and let's see if we can continue the proof. Let's just zoom out just a little bit so that we can see that commutator there still. There we go. All right, I'm going to switch colors just because this is a major turning point in the proof here. All right, so let's calculate the commutator H2, K1 to see if we can confirm that those commute. So the commutator of H2, K1 is H2, K1, H2 inverse, K1 inverse. When I say calculate, the calculation is done. That's it. That's the commutator. But now here's where we get to use what we know. Look at this. And think about what we know about that. That's a conjugate of K1. K1 is normal. We're conjugating with an element of G. That means that this thing here, this whole thing belongs to K. And we're multiplying it by something else from K. So this thing belongs to K. But then again, at the same time, what we have here is a conjugate of an element of H. H is normal. If we conjugate it with something in G, we still get an element of H. So that is an H. And of course, H2 is in H. So this commutator is also in H. Okay, wait a minute. This commutator is an element of G that belongs to H and belongs to K. So it's in the intersection of H and K. But the intersection of H and K was the identity. And that means H2, K1, H2 inverse, K1 inverse belongs to the identity subgroup, which means that this really is the identity. So the commutator is the identity, and thus H2 and K1 commute. So returning to what we were working on earlier, this means that H1, H2, K1, K2 is equal to H1, K1, H2, K2. And so, phi of H1, K1 times H2, K2, that is equal to phi of H1, K1 times phi of H2, K2. So phi really is a homomorphism. Okay, after that whole thing with, activating the commutator, the part about phi being 1-to-1 is going to seem kind of anticlimactic. I apologize in advance for that. But I think that'll make a nice little finish to this. Let's zoom back in. This thing's kind of sensitive sometimes. All right, so let's switch back to blue, I think. That's a good color for finishing the proof, I think. All right, so to finish the proof, let's suppose, I'm just going to move a little bit so I have a little bit more room to work. All right, to show phi is 1-to-1, we're going to use the kernel of phi. So we're going to show that the kernel of phi is trivial. Now remember, trivial is the trivial subgroup of the domain, which was H cross K. So that's just the element 1, 1. Remember, those are both the identity of G, because even though we're doing H cross K, H and K, they're both subgroups of G. So we just mean the ordered pair consisting of two copies of the identity of G. All right, so for this, suppose we have something in the kernel. Suppose that HK is in H cross K such that phi of HK is the identity of G. Identity of G there because we're mapping into the group G, specifically into the subgroup HK. All right, well then, that means, well, phi of HK is just HK. Phi of H comma K is HK. So HK is equal to the identity. So H equals K inverse. But now look at this. This is an element of H. This is an element of K. And they're the same. So there's this element which belongs to both H and K. So I'm just going to say H belongs to H and belongs to K because it's K inverse. So that means H belongs to H intersect K. But wait, H intersect K is the identity. It's just the trivial subgroup. So that means H has to be the identity. And also, we could use the same strategy on K inverse. K inverse belongs to H intersect K, using the same equation that we've just written. So K inverse is the identity. So K also has to be the identity, because we're just talking about the inverse of the identity. So what does that mean? So HK had to have been identity, which is what we hoped for. So the kernel of phi is trivial, and that makes phi 1-to-1. Therefore, phi is an isomorphism. We've done all the things necessary to show phi is an isomorphism from h cross k to hk. And let me just make one more remark here. One more remark. Let's zoom out one more time. I love how all these iterative zoom outs cause the text to get smaller and smaller. Okay, or bigger and bigger depending on your point of view, I guess. Okay, so one more thing. We showed h cross k is isomorphic to the subgroup hk, which is a subgroup of G. But we also talked in one of the previous videos about the condition where we say h times k is the entire group G. That's an additional condition we can have. So if hk is equal to G, that is, these combinations of elements of h and elements of k make up all of the group, then we also have a proof here, and I mean we've proven it. I'm not saying that we need to prove it separately. We've actually done this now. Then we've shown that h cross k is isomorphic to G itself. So if you find two complementary subgroups inside of G, whose intersection is the identity, trivial, both subgroups are normal, and the two subgroups, when multiplied together and combined, give you all of the group elements, your group, it's not really its own group. It's a direct product of two smaller groups. And I think that's pretty cool. All right, so that's it for this video. That's it for internal direct products.